Hey guys, how's everything going? Let's take a look at number what is 12549 minimum removal to make valid parenthesis. So I took a LeetCode contest today and it didn't went well. Didn't go well. I only accomplished two easiest problem. There are four of them. I only complete half of them and ranked top 50% of all the attendees. So it was a very bad result, but it was the first time I attended it. So well, I think I'll do better and better in the future. And meanwhile, I was going to take a Facebook interview next month. Technically, I have almost 1 month, 35 days to make my preparation. So I bought 1 month LeetCode Premium membership and find all the Facebook problem. So from today, I'm going to make some videos. First, it's about Facebook LeetCode problem, and second, some of the interview problem, like some basics of JavaScript, basics of the browser, basics of CSS, something like that. And I will also push some videos about that. So based on my naive calculation, I need to make at least 5 problems about LeetCode and 3 of the interview problems. Yeah, so I'm currently working on my plan. I hope I'm doing well. I will let you know what I'm going to be, what I am asked in the future. Maybe if I can, I shouldn't, but I will let you know how difficult are they and what types of problems, like about tree or about anything. Okay, so here is my first challenge, which is 12549 minimum removal to make a valid parenthesis. Okay, we're given a string s of parenthesis and lowercase English characters. Okay, my task is to remove the minimum number of parentheses so that the resulting parenthesis string is valid and to return any valid string. Formally, a parenthesis string is valid if and only if it is empty string, it's valid, contains only lowercase characters, it's valid, or it can be written as A concatenated with B, where A, B are valid string, or it can be written as parenthesis A, where A is valid string. So for example, we're getting this kind of string because all the parentheses are valid, so it is valid. We will be given, any valid string. Any valid string. So we could get this, or this is also okay. I mean, because originally the parentheses are not matched, right? So we remove this one or remove this one. Yeah. And the second one, this is not valid, so remove it. Okay. So this, all of them are not valid, so empty string is valid. And for this one, this one is not valid, so I remove it. Or actually, this could be also removed. I think I've done a similar questions before. It's about how to determine the combination of parentheses are valid or not. But during a real interview, I must not say, okay, I've done some similar question before, so I will start coding. That is not good. I think I need to express the basic how I approach this problem. Okay, so let's just analyze an example like this. The first thing is that the first characteristic comes to my mind, that is that the letters doesn't matter, right? The lowercase alphabets are actually doesn't matter. It doesn't matter what they are. It doesn't matter how many are they. Actually, we can reduce it down to like, okay, this is like a O, like A is O, OT, T is O, and then this is the same as 1, so O, okay, O, 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 right? And to make things more is string, empty string is valid. So actually, this similar is just to something like how we handle this, right? And then let's analyze this requirement. We're going to return the valid strings. There are a lot of cases that the strings is valid, but there is only one case. How to say? We can get the counterpart of this problem is when we can't define it is invalid. That means the parentheses are not valid. This is only case, right? If the parentheses are valid, we can just insert as many letters into this string as many as we want. So the counter, like invalid case, is equal to invalid parenthesis combination, right? So yeah, so when we traverse through the string, we can just keep track of the parenthesis and define whether it is valid or not. And then this reminds us another step. If we find some invalid string parenthesis pair like this, we actually can just crush it down like this, right? Remove it. It doesn't. So it's valid. So it doesn't matter anymore. So it's kind of like this, right? So it's for the invalid case problem. Yeah, and then we can remove another parenthesis. Like to be simple, we could remove this one, but we just remove the closest pair. So actually, we left the last. We get the last parenthesis, right parenthesis, and yeah, this is the invalid one. Okay. So during analysis here, we found that we could just crush down, remove the valid parenthesis pairs, and the rest of the parenthesis is the invalid ones. If we remove them, like this input, if we remove the last parenthesis, it's going to be a valid string, right? So our solution is clear now. And we remove, how to say, remove is not remove, but traverse through, go through all the parentheses, remove the valid pairs, the rest pairs, or the rest parents are invalid ones. And then remove the invalid one. Remove them. And we can get the valid string. So how would we achieve this? First, we find that every valid pairs must have one right parenthesis, right? So if we find a right parenthesis, we need to check if left one is valid or not, right? If it is, we move this supposed to, and then look to the second one. If left is not, if is like something like this, then we just say, okay, I'll wait another one, so this is invalid too. Right? Yeah, so actually this is a very typical stack, right? If we met the left parenthesis, we push it in. If we met the right, we check if we can remove it with top. If not, we push it in. And at last, we can get all the invalid parentheses in the stack. So this we can use a stack, and it will cost us what the time it is. When we met left, we pushed it in. When we right, we pop it, or we pop it together. We pushed it in, or pop it with the top element. So at most, it's 2 times, right? So the worst case is that we push every right parenthesis, all our right parentheses, and we push them in, and we will check it twice. So actually, it's big O n, right? Linear time. And we need to remove them. So this is another problem. So we find this invalid parenthesis, but how could we remove them? It might be any parenthesis. So yeah, we need to know which index are they. So the solution would be we stack with index. So the element in the stack is not the parenthesis or the parenthesis itself, but parenthesis and index. We can do it like this. And what does this cost us? We cost the extra space, but the complexity doesn't change. So the space would be the worst case is all the characters are pushed in, so it's linear. When we remove them, we need to collect the final result. How to remove them? There's another problem, right? How to remove them? We could traverse through the original array, and if we match the target index in the stack, we can ignore it and collect a new result. Collect a new result, right? But if we are going to check if index is into the stack, it's gonna be a search problem. That will be log n, right? It's not linear. It's not n. It's not constant. So to improve, we need to use another. We could we use a hash map to store the index after stack is generated. It means we we have three parentheses at the stack at the end. So we transform. We collect the index with on, big O-N. Worst, right? Big O-N. And then we can use hash map to determine if index is there or not, and then collect the result. This will cost us. We need to traverse every index, so it's still big O-N. So in total, it's 4. Yeah, times 4 of big O-N. Yeah, it's big O-N. I think it's or we cannot. We don't need to use this hash map. We can use 2 pointers, right? Because the index will be ascending. We can use 2 pointers. One is into the stack, and the other is into the original array. And if they match, we wait until one of them is matched. If matched, we move both pointers forward. So that will just we can make it without a hash map. And still, it is big O-N. This could be avoided. Use 2 pointers. Yeah, but this is a point. This is a part that I think we could do in the improvement part. So you don't show the interviewers that okay, I can do it perfectly. I just do it brutally and then try to improve little by little. I think this is the case I think I can handle. The most important step, we forgot that what the complexity is if we're going to do it brutally. I mean, if brutally, I need to. Wow, this is brutally is not. It's unimaginable. I mean, if I move this, I don't know, remove this one. Okay, so let's analyze the brute force one. It means remove each. Because when you're going to find the minimum, so remove each parenthesis. check if they are valid. So their worst case would be there will be n. This is the length of the word, n parentheses, right? For each, there will be possibility that they are there or not. So it's these kind of possibilities. And for each string left, if we need to determine if they are valid or not. So we need to go left to right and calculate the sum of left parenthesis and the right parenthesis. It will be big O n, right? So the time complexity would be like this. Wow, it's not acceptable. So we stop here. I will not continue it here. I need to improve by speaking loud of my thoughts with these steps. So now let's start to write the code. The first step is we created a stack to filter out the invalid parentheses. So we use a stack. I'll make it center. Okay, the stack is empty. I'll loop through all the string. Yeah, so if it is left parenthesis, we push, right? Remember, we push not only the parenthesis itself, but in index. So character index. If it's right parenthesis, okay, we say we check we pop the rightmost one. If rightmost is left, we just do nothing. Yeah, because it's already popped. And if it is not, it's right. Then we push both them in, right? We push rightmost, and also we need to push character. And at last, at last the characters, the parentheses in the stack are all invalid, right? Yeah, now what we do, we need to filter out the substring. We could add a little check here. If it is already valid, we can return fast enough, right? So if stack length is 0, I'll just return S itself. Now if there is invalid parenthesis, I think collect the value string with 2 pointers. I use 2 pointers here. Let p stack equals 0. Let p s equals 0. So okay, I'll just do for loop here. Let p s equals 0, ps more than s.length. We loop it through. Const result. If ps is not equal to p stack, we push it in, right? We push this element. And then if it is, we do nothing. We just go to next one. But we need to push stack forward, right? Forward, and if the p stack is valid, right? Stack. Yeah. If p start length, if p stack is valid, I mean if still there is something in the stack, we push it, and if it is met, we skip it but move to the next one. Okay, finally we return result join empty. I think, yeah, empty. We need to analyze all the complexity here. Yeah, this space is big O n. N means the length of the string. This will be time, linear time, and this will be okay, and this is okay, and this would be time on, the results, space, big O-N, and then if this is, we move, so this will be another, we use join, but I think internally it still use time O-N to join them up, right? So in total, it should be time should be on, space should be linear also. Let's try it run the code. I hope it pass. It's not. Of course. So what's the problem? I need to analyze the code within my mind again. Okay, we have a stack. We traverse through all the string. It's okay. We get the character S, right? Yeah. If it is left, we pushed it in. Oh! You see? We pushed it in. We push rightmost. We pop. But first, if we pop, there might be nothing there. If there's nothing, it means it's nothing. I say it is undefined. I will push the right in, right? But with the index, I forgot to add the index. And if there is the right, and I say rightmost 0 is if it is left, parenthesis, we do nothing. If not, we will push back it in, and also we will push character in. And then we check stack, but here we're not comparing PS to P stack, okay? You should compare it to P stack, and the index should be the second element. So add the index 1. So we push SPS. Yeah, this should work. Still, it's not working. PS. Okay, we get PS. Right. P stack plus 1. Okay. Finally, we return the result. We log the stack. So what do we have in a stack? We actually have this one. So so the stack is actually right. If Ah, I see. We have mistake. We have a mistake here. This actually doesn't is not right. We only skip for the when the elements in this is in the stack. For the other cases, we were all pushed in. So if it's in the stack and PS is equal to the index, we skip. Wow. For other cases, we push. Oh, we got a result, but it's not right. Zero, 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we remove 12. So this should be 12. If stack, my god. Oh yeah, I think we're accepted. Hopefully, yay! But we are not fast enough, man. Is there still anything we can improve? I'll try this for another, because we already recorded this video for about half an hour. I'll take another 10 minutes to try to improve. If not, I will give up, okay? So, is there another way we could make this faster? The first, we use a stack, and for the stack part, is this good? We might be. Let's just have a try. Maybe we could use some built-in method. We could we could just don't do this. Okay, I'll do some tricks. We split all of them. It's not okay, I think. Yeah, it's not. I think is this better if we use a hash map? Actually, it is not. I think one case is that we could use string slice. But slice actually, internally, it will use extra time complexity, right? So actually, we could get the index and slice them. Let's try that a little bit. So we will not go through all the letters, but let P is 4. What is it? So if it is 0, we need to splice 0 to 0. 0, 0. So it's empty. And if this next one is 1, oh yeah, so actually for P I'll use another solution. Const result equals this. For that P equals 0, P is smaller than stack. Push if p is 0, I say slice 0p. No, stack p 1. If not, slice stack p minus 1, 1. Stack p 1. And finally, we return a join. Should work also, right? No? Missing argument slice 0. Ah, my bad. Slice. Yeah. Maybe a little faster. It's wrong. What? We sliced it. If p equals 0, p is plus, right? And we push, because p is not 0, we will slide previous one until this one. Ah, my bad. So it should be plus 1. The input is this. Oh shit, why? The stack is right according to our previous submission. P 0, go to stack content, push. If 0, we slice 0 to that part. It means here. And then the rest, my god. And finally, god, we need to p now comes to the last one, so p stack p, yeah, this is right, p 1 plus 1 as slice. Still p is not defined. Let p, god, let p, shit, still not right. Property 1 of 0, undefined. P stop length. My god, yeah. Finally, let's submit. Wow, we're faster than 99%. Well, I'm not, but actually the time complexity here doesn't matter that much because we're using a built-in method of slice. So technically, in a interview, this doesn't mean it's meaningless. I think the previous solution will be good enough, and just talk to convince them. Yeah, so that's all for this problem. Yeah, I hope it helps. See you next time. Bye bye.